Welcome back to the Explainer. I am absolutely thrilled you're here today because we're going to take the sheer poetry of motion and translate it into the precise, totally predictable language of mathematics. We're diving headfirst into kinematics, which is really just the study of how objects move. Whether you're looking at a sprinter exploding off the starting blocks, a single raindrop falling from the sky, or a sports car tearing down a straightaway, this explainer is going to give you the exact foundational tools to map out their journey step by step.
All right, to really get things rolling, we need to take a quick trip back to 16th century Italy. Picture the magnificent Leaning Tower of Pisa. Now, before a guy named Galileo Galilei came along, it was basically just considered common sense that a heavy object would fall faster than a lighter one. I mean, people were mostly observing things like feathers fluttering down and fighting against air resistance. But Galileo, he had this radical hypothesis. He said that in the absence of air resistance, all bodies fall with the exact same constant acceleration. Legend actually has it that he dropped different masses straight off this very tower just to prove it. It's honestly the perfect historical hook as we explore freefall and acceleration today.
So here's our roadmap for this explainer. We'll start with the language of motion, then look at graphing motion, and unpack the kinematic equations. After that, we'll tackle freefall acceleration, and finally, we'll wrap up by mastering projectile motion.
Let's jump right into section 1, the language of motion, looking at scalars versus vectors.
Now, in our day-to-day lives, we tend to throw around words like speed and velocity, like they mean the exact same thing, right? Well, physics is a bit more demanding. There's a really vital dividing line between scalars and vectors. A scalar, think distance or speed, only cares about the magnitude, basically just how much or how fast. But a vector, like displacement or velocity, it absolutely requires magnitude and a direction. Let's say you're on a bike. You ride 500 meters straight east down a road, turn around, and pedal 300 meters back. Your total distance traveled? Sure, that's 800 meters. But your displacement? You're actually just 200 meters east of where you started. That little distinction? It's literally the bedrock of kinematics.
I actually wanted to highlight this specific quote directly from our source material. In ordinary language, there is no difference between the terms speed and velocity. However, in physics, there is an important distinction. It hits the nail on the head. Because distance and displacement are completely different beasts, your average speed and average velocity can be wildly different too. Going back to our cyclist, if that whole ride took exactly 120 seconds, their average speed was a solid 6.7 meters per second, but the magnitude of their average velocity, just 1.7 meters per second. So getting these terms right isn't just about semantics, it literally dictates the math we're going to use.
And this need for precision brings us perfectly to acceleration. Acceleration is a vector that measures the exact rate at which velocity is changing over time. And since it measures a change in velocity, which is a vector, acceleration has to be one too. It's got a specific direction. Say a car absolutely floors it, going from a standstill to 19 meters per second in just 6.3 seconds. That's a positive acceleration. But if a train slams on the brakes and slows down over a minute and a half, its final velocity ends up being lower than its initial velocity. We get a negative change, resulting in a negative acceleration, which, we usually just call deceleration.
Moving right along to section 2, graphing motion and visualizing the data.
So, how do we take all these abstract concepts and actually picture them? Well, the cool thing is, a motion graph is basically telling you a hidden story. If you're looking at a graph showing displacement on the vertical axis and time on the horizontal axis, the steepness or the gradient of that line gives you the exact velocity. You just draw a tangent to the curve, find its slope, and boom, you got your instantaneous velocity. Now, if you look at a velocity time graph, the gradient of that line reveals the acceleration. And here is the really beautiful part. If you calculate the area trapped underneath that velocity time graph, maybe by adding up the triangles and rectangles under the line, that area gives you the object's total displacement. It's like a giant puzzle where all the pieces fit together flawlessly.
Next up is section 3, the toolkit, where we introduce the kinematic equations.
Okay, we are finally ready to build the famous kinematic equations. But hey, a really important disclaimer here. This math only works when acceleration is uniform, meaning it stays completely constant. These 5 equations are essentially your ultimate cheat sheet. They rely on 5 specific variables: initial velocity u, final velocity v, acceleration a, displacement s, and time t. To crack any linear motion problem, you just list out the quantities you already know, figure out what you're trying to find, and select the equation from this table that matches those exact pieces. Like if you don't know the final velocity and you honestly don't need it, you'd use s equals ut plus 1/2 at squared. It's wonderfully logical and immensely powerful.
Let's see this in action with Section 4, Freefall Acceleration, or Gravity at Work.
Let's apply these equations to the real world. What you're seeing here brilliantly illustrates how we actually measure free fall today. By flashing a strobe light at a set frequency, like 20 times a second, we can photograph exactly how a falling ball speeds up downwards. Alternatively, dropping a steel sphere through electronic light gates lets us time its fall with incredible precision. Both of these methods allow us to calculate the exact uniform acceleration near the Earth's surface caused by gravity. We call this constant g, and unless you have some serious air resistance, literally everything dropped near Earth accelerates downwards at a constant 9.81 meters per second squared. Turns out, Galileo was absolutely right all those years ago. Which brings us to our final stop, Section 5, Projectile Motion, Mastering 2D Parabolics. Up until now, we've basically just been looking at stuff moving in a straight, one-dimensional line. But what happens if you throw an object forward and upward at the exact same time? Well, the absolute secret key to unlocking two-dimensional motion is realizing that the vertical drop and the horizontal forward movement have completely nothing to do with each other. They are totally independent. You just split the initial launch velocity into a horizontal x component and a vertical y component. You apply gravity strictly to the vertical side to figure out how high the object goes and how long it hangs in the air. Meanwhile, because gravity only pulls straight down, there is no force accelerating the object horizontally, which means the horizontal speed stays completely constant for the entire flight.
And we can see this exact math playing out on the pitch. Take a cricketer bowling a ball. The split second that ball leaves his hand, it becomes a projectile. If we know the initial angle and the speed of the release, we can predict exactly where it's going to bounce. The upward vertical part of the throw fights against gravity, eventually slowing down to zero at the absolute peak of the arc and then speeds back up as it falls. Simultaneously, the horizontal component is just steadily, calmly carrying the ball forward over the pitch at a totally constant rate. Combined, they trace a mathematically perfect curve.
Now, if you take our kinematic equations and use them to find the absolute maximum horizontal distance, what we call the range of a projectile launched from level ground, you get this beautiful, elegant little derivation. R equals the initial velocity squared times the sine of 2 theta, all divided by gravity. And here's a really cool insight. Because the maximum possible value for a sine function is 1, and that happens at 90 degrees, we can see mathematically that the maximum range is achieved when 2 theta is 90. Meaning you should launch an object at exactly 45 degrees if you want to throw it as far as possible.
You know, you can actually see this physics happening right in your own backyard. Notice how the water jets from this garden sprinkler form these gorgeous, totally predictable curves? That shape is called a parabola. It's literally the physical manifestation of our kinematic equations right before your eyes. Constant horizontal velocity perfectly layered on top of vertical acceleration due to gravity.
But to wrap up today's explainer, I want to leave you with a real-world curveball. Throughout all our equations today, we very conveniently assumed that air resistance just doesn't exist. But think about reality for a second. Imagine a feather or a cricket ball pushing through a really heavy headwind. If our equations predict a mathematically perfect symmetrical parabola, how do you think air drag actually alters that trajectory? Does the ball land short? Does the curve change its fundamental shape entirely? I really want you to think on that as you look at the world moving around you. Thanks so much for joining me on this explainer, and keep exploring.